Kuzampu. Welcome to Bhutan e-learning program. My name is Mohan Setri, and today I'll be taking you through chemistry relation for key stage 5, that is for class 11 and 12. In today's lesson, we'll continue the same chapter, that is electrochemistry. We'll be going through, we'll be studying part 2 of the same chapter, electrochemistry. In the previous lesson, we have looked at various parts such as definition of electrochemical cell, construction of electrochemical cell, working of electrochemical cell, electrode potential, standard electrode potential, etc. Now, in this lesson, by the end of this lesson, we will be able to define the EMF of a given galvanic cell and explain the application of inert values. Standard EMF of a cell. Now, when we construct a cell, then how do you determine the EMF of a given cell? So, in order to calculate the EMF of a given cell, E cell equals to E cathode plus E anode. Because we have two electrodes there, we will be taking E cathode value and E anode value. Now, as we know that in cathode, reduction takes place. So when you take this, when you use this formula, we will take the reduction potential value of cathode electrode and oxidation potential value of anode electrode. But as we have studied in the previous lesson, that the standard reduction potential of a given electrode is taken as standard electrode potential. Therefore, if you take standard reduction potential value for both the electrodes, then we'll use E cathode minus E anode. In this case, we are taking reduction potential value for both. Now, when you use minus in front of reduction value, in front of the electrode potential value of anode, it automatically gets converted into oxidation potential value. So, even though this is the basic concept, finally, when we do the calculation, most of the time we'll use this last equation for calculating the EMF of any given cell. Okay, let's look at this question. Calculate the standard EMF of the following cell. So, E naught here stands for standard. So, calculate the standard EMF for the following cell. We have copper, which got oxidized into copper ion, and silver ion, which got reduced to silver metal. And then standard reduction potential of each electrodes are given. And as you can see here, both copper standard reduction potential is given, and for silver also standard reduction potential is given. Now, let's solve this question using the board here. So, formula E naught of a cell equals to E cathode reduction potential value minus E anode, again reduction potential value. So, as you can, I'll copy that question here. Copper is getting oxidized to copper ion, and silver ion is reduced to silver metal. Now, here we know this is cathode. So, what's the standard reduction potential value of cathode? Is given E naught silver equals to 0.80, which is given in the question, and E naught copper reduction potential value of copper equals to 0.34 volt. So, let's substitute this in the equation here. So, we know that copper is cathode, silver is cathode here. So, we'll take the value of silver here first. So, it is 0.80 volt minus, now let's look at the value of copper. It is 0.34. So, 0.34. So, when you do this question, solve this question, we get 0.46 volt. So, this is the EMF of the given cell. I hope you understood this. So we are substituting in this formula. E naught equals to E cathode minus E anode when we take the reduction potential value for both the electrodes. Now, this is a method, this is a formula which is used to calculate the standard electrode potential. When I say standard, it means when all the conditions are in standard form, that is, concentration is 1 molar, temperature is 298 Kelvin, and pressure is 1 atm. Now, what if the cell is not in standard state? What if the cell is not, the concentration of solution is not 1 molar? Then for such cell, we use different type of equation for calculation of EMF of such cell, and that is known as Nernst equation. According to Nernst equation, EMF of a cell equals to standard EMF of a cell minus 0.0591 by N. Here N stands for number of electrons that is involved in the given redox reaction, log oxidized state by reduced state. So using this equation, we'll solve some questions. So let's look at that first question. Calculate E cell at 25 degree for the following reaction. And reaction is given, standard electrode potential of both the electrodes are given. Now, please try yourself. I'll give you some time. Use the formula that's given in the previous slide and solve this question. I hope by now you must have got the answer. Let me solve and then let's check our answer whether they match or not. So the formula is, as per Nernst equation, EMF of a cell equals to E naught, standard EMF of cell, minus 0.0591 by N. N is the number of electrons involved in the given redox reaction, log oxidized state by reduced state. Now let me copy the question from there. Zinc is oxidized to zinc ion, and the concentration of this zinc is 0.50 molar. And we have copper 2 plus, which is reduced to copper. The concentration of copper 2 ion is 0.2 molar. So one, we have 0.5 and we have 0.2 molar. And again, additional information that's given here is standard electrode potential of zinc, Zn2 plus to zinc equals to negative 0.76 volt, and standard electrode potential of copper 2 plus to copper equals to 0.34 volt. Now let's substitute there. So first thing that we need to find is E naught. So let's find E naught. As you have seen in previous slide, E naught equals to E cathode reduction value minus E anode, again reduction value. This is the formula to calculate E naught of a cell. Now let's look at, is it reduction? Yes. Is it reduction? Yes. Now which one is cathode? From the equation we know that copper is cathode, so I'll take copper first. 0.34 volt minus 0.76 volt. Hence, I'll get 0 together. So minus minus becomes plus. So it will be 1.1 volt. So this is E naught value. Now I'm going to use this E naught and substitute it in the equation there. So I'm writing here E naught value that I got is 1.1 volt. Now E equals to E naught minus 0.0591. Now N, how many electrons are involved? It is losing 2 electrons and it is getting 2 electrons. So the value of N here will be 2. Value of N is now replaced by 2. Log oxidized state. Which one is oxidized? Let's look at this one. Zinc is oxidized. So I'll take the concentration of zinc here, 0.5. What is the concentration of copper, which is reduced? 0.2. So I'll substitute this also. E naught value is 1.1 volt. So now when you put this in calculator, we'll get like this. So when you put this one, you'll get 1.1 minus, when you divide 0.0591 by 2, you'll get 0.02955 log. Now when you do this one, it will be 2.5. So final answer you'll get is, if you substitute all this together, you'll get 1.08 volt. So this is our answer for this question. So we have to use Nernst equation if the cell is not in standard state, and we can calculate the standard EMF only if the cell is in standard state. So this is the solution for first question. For second question, I'll just give a hint. You'll try yourself. Now, let me copy this second question. Zinc is oxidized to zinc ion, and the concentration of this one is 0.1 molar. We have salt bridge, and 2 silver ion is reduced to silver. This is the information given in the question, and we also have this one, standard reduction potential of zinc is equals to negative 0.76 volt, and standard reduction potential for silver equals to 0.80 volt. Now, let's look at this one. Let's look at the concentration of silver here. It is 0.2. Is it in standard state? No, because they have different concentration. If it is in standard state, the concentration of both half cell, the solution, concentration of solution present in both half cells should be 1 molar. So it's not the case. Therefore, we have to use Nernst equation here. So again, Nernst equation, as per Nernst equation, E equals to E naught minus 0.0591 by N log oxidized state by reduced state. So first let's find E naught here. E naught equals to E cathode minus E anode. And in this case, we will be taking reduction potential value. So cathode is silver, so which is 0.80 volt minus 0.76 volt. So E naught we get as 1.56 volt. This is the standard EMF of this cell. Now let's substitute this in Nernst equation now, in that equation. So when you substitute this, E equals to E naught, I got it as 1.56. 1.56 minus 0.0591 by. Now I know you will have some confusion here, because here how many electrons are involved? 2 electrons. Here when you take only 1 silver, it is consuming only 1 electron. But since we are taking 2 silver, the 2 electron that is released from here will be consumed by 2 silver ion. 1 silver will take 1 electron and another silver will take another electron. Therefore, N will be 2 here. So please don't get confused. Don't think that here since plus 1, N will be 1. No, N will be 2. That's why we are balancing this equation. Now log oxidized, zinc is oxidized, concentration 0.1. Fine. Is there any number used for balancing the equation? No. So fine, keep it as it is. Now reduced state, the concentration of reduced state is 0.2. But here in this case, we have to take 0.2 to the power 2, because you have balanced this equation. 2 molecules of silver ion is involved in the equation. Therefore, that number that is used for balancing the equation will go as power. Therefore, you will get the answer using this one. So I hope you get the clear idea how to calculate the EMF of cell. While using Nernst equation, you have to balance the equation. And while balancing, if you have any number in the equation, then that number should go as power of that concentration. Now we look at the application of inert values. So there are so many applications of inert values, out of which the first one is to check the feasibility of a cell reaction, check the feasibility of a redox reaction. Now any reaction, if the net EMF value is positive, then the cell reaction is feasible. Cell reaction is feasible. But if the net EMF value is negative, then the cell reaction is not feasible. If the cell reaction is not feasible, then how do we correct them? We have to interchange. We have to make cathode as anode and anode as cathode, then we'll get positive value. If we get negative value, then that cell reaction is not spontaneous. It is not feasible. It will not take place. Therefore, we have to rectify that by reversing the anode into cathode and cathode into anode. So that is first application of inert values. Now let's look at second application, that is oxidizing and reducing power of elements. From the slide, as you can see here, oxidizing power of an element is directly proportional to standard reduction potential value, whereas reducing power is directly proportional to standard oxidation potential value. So let me explain this briefly here using the board. So as you can see here, zinc and copper. So zinc and copper ion. Now here it becomes zinc is getting oxidized to zinc ion and copper is reduced to neutral copper metal. Now let's look at those values. Reduction potential value of this one is negative 0.76 volt and reduction potential value of copper is 0.34 volt. Let's look at this one now. Now here zinc is oxidized. Zinc is oxidized, but zinc is acting as a reducing agent. Why? Because it is donating electron and helping copper to get reduced. Therefore, it depends on its oxidation potential. So it is oxidative. So that's why oxidizing power, so this is reducing power. So reducing power is directly proportional to oxidation potential of zinc. Now, if you look at copper, copper is reduced to neutral copper metal. Copper is reduced to neutral copper metal. But it is helping zinc to get oxidized by accepting its electron. So copper is oxidizing agent here. Copper is oxidizing agent because it's helping zinc to get oxidized. Now, oxidizing power of copper will depend on reduction potential value. That's why oxidizing power depends on reduction potential value and reducing power of an electrode depends on oxidation potential value. Now, let's look at third application of inert values, that is comparison of reactivity of metals. Now, when you have so many metals, and if their inert values are given, then how do you identify which metal is most reactive and which metal is least reactive? So, metal, they undergo oxidation. So, for metal, reactivity is directly proportional to oxidation potential, or it is inversely proportional to reduction potential. Reactivity of metal, again, let me reiterate that metal undergoes oxidation. Therefore, reactivity of metal depends on oxidation potential. In other way, reaction of metal is inversely proportional to reduction potential. So, if you have 4 or 5 metals, the elements having lowest reduction potential will be most reactive, and the element having highest reduction potential will be least reactive. Let me give this example here. So, if you let's take zinc here, let's take nickel, let's take copper, and let's take silver. So, reduction potential values for these elements are, so for zinc, standard reduction potential of zinc is negative 0.76 volt. For this one, it is negative 0.25 volt. For copper, it is positive 0.34 volt, and for silver, it is positive 0.80 volt. Therefore, if you look at this one, zinc has the lowest reduction potential. Therefore, it is the most reactive metal. Silver has the highest reduction potential. It is the least reactive metal among these elements. So, please remember that reactivity of metal is directly proportional to oxidation potential and inversely proportional to reduction potential. Now, fourth application of inert value is displacing power. Now, displacing power, when I talk about displacing power, it is more or less related to reactivity. Always, more reactive elements will be able to displace the less reactive one. It's always that case. So, that we know that the element having lower reduction potentials are more reactive. Therefore, those elements which have lower reduction potential has higher displacing power than those elements which have higher reduction potential value. Now, let me explain this with one example. Let's keep these two. Let's take zinc and copper. Now, these two values are there. Now, I am taking a beaker here. In this beaker, I am taking zinc sulfate solution, and to it, I am adding copper granules. What will happen? Now, can copper displace zinc from here? Let's look at this reactive. Which is more reactive? Zinc is more reactive. So, therefore, copper cannot displace zinc from zinc sulfate solution. So, here no reaction will take place. No reaction will take place here because copper cannot displace zinc from zinc sulfate solution. But let's take another example here. Let's assume we are taking copper sulfate solution, and to this copper sulfate solution, let's assume that we are adding some zinc granules. Now, what happens? Let's look at this one. Which is more reactive? Zinc is more reactive? Yes. So, what happens? Now, zinc being more reactive will displace copper from copper sulfate solution. As a result, you will get, if you look after some time, you will not have zinc copper sulfate there, but instead of copper sulfate, you will find zinc sulfate. Because zinc plus copper sulfate will give us zinc sulfate and copper will get displaced. Now, there is another application of this concept again. Using the same concept, I'll just explain. Now, can I use zinc container which is made of zinc to store copper sulfate? Can I store copper sulfate solution in zinc container? Then let's look at this. No, we cannot store. Why? Zinc is more reactive. If we store like this, zinc being more reactive will go inside, displace copper from this solution, forming zinc sulfate, and copper will get displaced. So we cannot store. So whenever you store, the solution should be more reactive than the container. If container is more reactive than container, from container the metal will come in, displace cation from the solution, and form a new compound. So these are basically the 4 applications of inert values. So with this, we have come to the end of this lesson. Before we wind up this lesson, let's revisit some important points that we have discussed here. So first one, EMF of the cell at standard and non-standard conditions. So for standard, we use the formula E naught equals to E cathode minus E anode when both electrodes reduction potential values are taken. And when we call a cell, when we say that the cell is in stand state, when the concentration is 1 molar and temperature is 298 Kelvin. But if these conditions are not fulfilled, then these cells are known as non-standard. If the cell is in non-standard condition, therefore, we will calculate EMF of a cell using Nernst equation. And lastly, we have looked at the application of standard electrode potential values. We have discussed 4 applications here. Let's go through a few questions, and then you'll try to answer yourself. First question that we have is, you are provided with zinc granules, copper granules, and dilute HCl to prepare hydrogen gas in the lab. Which metal should be used to produce H2S gas? And explain. So we will be using same concept here. Second question, and then there also you can see standard reduction potential of both the metals are given. Second question, can a solution of 1 molar copper sulfate be stored in a vessel made of nickel? And you can see, just a hint, copper, standard reduction potential of copper is 0.34, standard reduction potential of nickel is negative 0.25. So you know from among these 2 metals which one is more reactive. If you know which one is more reactive, then you'll get the idea what will be the answer. And lastly, the last question that we have here is, the standard electrode potential of 3 metals A, B, C are negative 1.2 volt, positive 0.5 volt, and negative 3 volt respectively. Arrange these metals in the increasing order of oxidizing power. So with this, we have come to the end of this lesson. Thank you and have a great day. See you in next lesson.